Welcome to this class on using DevOps to build verifiably secure systems. My name is Bob Aiello, and I'm glad to have you join us today. I'm a consultant, practitioner, and I've been doing this for a very long time, a lot longer than the 25 years on the screen. I've written many articles and quite a few books on the subject of configuration management, application lifecycle management, and what lots of folks are calling DevOps since 2009. I'm very much involved with writing industry standards, and we'll talk a little bit about that today. I'm tools and process agnostic. I'm not an academic. I'm the guy you call in the middle of the night when that release doesn't work, although many of my books are used in graduate programs in computer science. So I kind of span academia and being a hands-on practitioner. Now, I've been very much leading the effort to write an industry standard focused on this methodology called DevOps, which we'll talk about today. And just a few key points about the standard itself that I think is going to impact the way a lot of systems are developed. We focus a lot on principles and practices to build, package, and deploy systems and applications in a very reliable and secure way. In fact, a verifiably secure way. How do I actually make sure that I can prove that the system is reliable and secure? We very much focus on having effective compliance and IT controls. There are federal laws that govern how you do banking systems, life support systems. Think of a hospital in a hospital system, or other types of mission critical systems that can affect many people's lives. We're going to talk about some of the principles in DevOps: mission first, customer focus, something called left shift, continuous everything, and systems thinking, and we'll consider who the stakeholders are. And most importantly, the fact that when you work with industry standards and frameworks, you're really aligning to other best practices. In our case, with full life cycle standards such as 12207 and 15288. So our goal is to build systems that are verifiably secure, reliable, and defect free. And we'll talk more about what that means. But you'll find many folks will say that there's always a trade-off between security, reliability, and defect-free systems versus, say, productivity and the cost. And that's to some extent true. But in this session, I'm going to be focusing on showing you how to provide systems that are verifiably secure, they're reliable, and defect-free. And 100% reliability is quite doable. And when you consider that software runs things like nuclear power plants and, again, life support systems, we do have situations where they have to be 100% reliable. So what does quality mean? One of the great thought leaders on quality was Joseph Juran, and he said quality consists of those product features which meet the needs of customers and thereby provide product satisfaction. So if your customer is happy, that's very much the whole point of quality. And quality consists of freedom from deficiencies. If you have got a lot of defects in your system, well, it's not going to be a quality system. Another thought leader was Edwards Deming. And Deming said the consumer is the most important part of the production line. So it's not just the folks who assemble whatever it is that you're receiving. Quality should be aimed at the needs of the customer, present and future. And quality begins with the intent, which is fixed by management. It's translated by engineers and others into plans, specifications, tests, and production. That's your whole life cycle to create whatever it is you're creating. And that's true whether you're working with an agile methodology or iterative waterfall methodology or systems lifecycle. There's always some sense of creating specifications for what you're going to build, some verification, and then pushing it into production. So how do we build quality in? So Deming said quality is already built in, must already be built in really before a customer complains. So Deming was thinking ahead, and understanding what folks complain about is important, but it kind of gives you a biased picture of performance. So we really want to start by saying, how do we build systems that are verifiably secure, reliable, and give you the right level of quality. So this methodology called DevOps is very much taking the industry by storm. So it's a new term. 2009, some colleagues went to a conference and kind of started talking about this. It's technically a portmanteau, which means we took two words, development and operations, we stuck them together, came up with a new word. It's very much about agile systems administration, agile operations, and a group of principles, but that doesn't really give you a good feel for what DevOps means. DevOps is development focused on delivering new functionality, which very much conflicts with the operations focus, which is on providing reliability. So developers want to fly forward. They want to deliver you new features. We sometimes liken them to be in the wild, wild west, whereas the operations team is more focused on having the system up and having reliable services. And this is all about how do we manage risk? In other words, I want to deliver new functionality, but I also want to make sure that that financial system that transfers your money into your bank account is reliable and doesn't accidentally put the money in somebody else's account, right? That's kind of important. So one time I was asked to break the rules, and I give you this example because it kind of gives you a feel for the conflict that each one of us can find ourselves in. I was running the build engineering team, which consisted of me and one other fellow, and we worked very closely with the testers, and we found that the system had some defects, and those defects were fixed. And the head of development came to me and said, look, we don't really have time to retest. We patched the defects we found, just push it right into production, which kind of breaks the rules. You're always supposed to develop, test, and then push whatever you tested into production. And I said to him, well, we really should go through another test. It might take us a few days. And he said, no, 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 no. If we don't meet my deadline, I don't get my bonus. So you just have to push it into production. So I had this conflict of interest where a very influential manager was pushing me to release code to production that wasn't retested after there were changes to it. So there's always this conflict of interest between developers and operations, and truly between other stakeholders from information security, including the end users. So each of us have a different perspective. And what DevOps does is it gives us an approach that helps us understand what those different perspectives are. So DevOps is also merging best practices, it's collaboration, it's both applications and systems development and deployment. So what does that mean? If I'm writing a new application, that's one approach. If I purchase a system off the shelf that I customize, that's more of what we call a systems development effort. And there's also not just the application layer, but the underlying infrastructure or the systems that the applications run on. So we have to consider both the application systems that we purchase and customize, as well as the underlying infrastructure. So security is really an important consideration. You might want to start by asking yourself, what makes a system not be secure, right? So I often joke that you can consider a system being insecure if a hacker penetrates it. Well, that's certainly one sign that you've got a problem. If information is exposed, let's say you have confidential information, most folks don't want to have their credit cards exposed, yet that has happened in quite a few major systems. If unauthorized transactions have occurred, which I think many of us have experienced that with large vendors, and large vendors will largely just force the consumer to take the hit on that. They won't even roll back the transaction in many cases. The system can be used to attack other systems. And of course, ransomware has been a common problem where a system is shut down unless you pay the hacker a sum of money to give you back control of your own system. So there's many vectors of attack. And if you want to really understand this stuff, then you have to take that approach of really taking a full systems view of how systems are compromised. So we often say that a chain is only as strong as its weakest link. So if I have a system that the front end is very secure, the back end where I do all my transactions is very secure, but I interface with a couple of other systems that are not so secure, that may be a way that the system can be penetrated. And that's happened in many cases. Lots of folks will also take the view of, well, it's not my code, it's just a library I pulled down from the internet. So a lot of times if you pull down libraries from the internet, they are not secure, and we have to identify those and either not use them, or in some cases, if we upgrade to a later version, we can have a little more security. So different approaches or vectors of attack is important to understand. So there are also situations where um, folks can break into a system through a connected system. There was an example of where a large retailer had their credit card system compromised, and the way the hackers got in was not through the retailer part of the system. They got in through the environment physical store environment system. In other words, the system that controls the temperature in the store was not well protected, and it wasn't segregated from the part of the system that controls your credit card. So they got in. They should have only been able to make the store a little hotter or a little colder, but in reality, they were able to get from that part of the environment physical environment monitoring system over to the credit cards. So they get in through a connected system. And sometimes social engineering or even a inside job, it could be a disgruntled employee. So with all these vectors of attack, and these are just a few examples. There's really many, many more. What can we do? Well, our approach has to be a full life cycle approach. You have to consider how you create requirements. You have to be able to consider your testing approach. And testing has to be very much a continuous effort. So you can have unit testing in the beginning, you can have integration testing, you can have functional regression testing and non-functional testing. We'll talk a little bit more about that, how we design the system, our practices when we develop and deliver. So you can't just try to tack on security at the end. You have to take a full life cycle approach and consider security from, from the whole life cycle, the whole effort to create this system. So security has to be built in. Those requirements, the testing, we do penetration testing at the end. That's necessary and it's important to do, but it's at that point, it's often too late to make the system secure. So you really have to start thinking about, and this is what we talk about when we consider a technique known as left shift, where we start to do the right things earlier in the process. And we'll talk about that throughout this presentation. It's one of the key DevOps principles of left shift, doing things earlier in the process that a lot of times folks try to tack on at the end. It's much more effective if you start building security in from the very beginning. So one of the considerations is for every requirement, do I have a test case to prove that the requirement was met? So I have to consider functional. In other words, how does the system function? Non-functional, which an example of that is the performance, as well as security. We have to consider what's the user experience? What's that user interface? Is the screen easy to navigate? Is it responsive? When I look at it on my handheld, does it act the same way if I look at it on my PC or tablet? So that user experience is very important. The back end processing. If I go to do a transaction, it takes forever to come back. I'm closing the tab and going somewhere else. So we have to also really consider about being verifiable, right? So that's where building test cases to match each requirement helps us verify our requirements that we designed. So for every requirement, we really need to have test cases from the beginning of the process. So we talk a lot about test-driven development. where we actually build the test harness in advance of writing the code. And that's a very effective technique. You also need automation. If you try to do your testing manually and you adopt these DevOps practices, and I'm going to talk to you about today that we are talking about, you're just not going to be able to keep up with the velocity. So automated testing is an absolute must-have. Unit integration testing, in other words, you integrate two components. They're written by two separate development teams. You have to integrate them. You have to get them to work together, and you have to do integration testing. Functional refers to new functions that you're creating. Regression testing is really about making sure that things did not break that were previously working. And as I mentioned, non-functional testing can include things like performance testing, performance under load. If it's a tax system, does it work during the year as well as on April 14th? Everybody's trying to use it at the last minute. You can't have the system break down on the most important day of the year. So verifiable systems is really key. When you look at the system, you have to consider it end to end. Too often folks say, hey, the main part of the system, the thought engine works great, or the interface works great. You have to consider the system as a whole. You have to take a full systems view, including whatever systems you connect to, or what we call downstream dependencies. So if you purchase something on my website and I hand off the processing of your credit card to another vendor because they do a great job of it and they handle all the security, that's pretty common practice. But if that vendor is down, then I'm not going to be able to sell anything. My system might be great, but if I hand off the credit card processing and that vendor is down, then it's as if my system is down too. So downstream dependencies are very important. And today's cloud-based approach, you have to consider the fact that if the cloud service is down, then your system is down. So that doesn't happen a lot, but it can happen. Cloud-based vendors, cloud-based providers often say they don't have 100% reliability. They have 99.9 or 99.5%, which means some hours during the year, the system may be down. Well, it turns out that a technique called cryptography is really going to be key, and I'm going to explain how that works. And it'll help us verify that our system is working. So we're going to start with the build pipeline. When we take the source code that our developers write to build our system, we have to make sure that we can track what version of the code went into a particular release. That's called tagging. So the code is tagged. We have to have what are called automated build procedures. That takes the source code and creates runnable objects, what we call derived objects. So they're derived from the build process, and that's how you get these binaries that can run on a computer, which are derived from the source code and the build process that the developers created. We often talk about configuration items. Those are the different derived objects, as well as the configuration files or any other runtime dependency that is part of the system. And we have to be able to deploy the packages that are holding all those configuration items to the production system. So I'm kind of getting into some of the details now. I have a developer who writes the code, but I have to actually make sure that whatever that developer wrote is built properly, is tagged so I know what version it is, because maybe I have to go back and fix a bug. And then I have to make sure that exact version of the code gets to production and we can verify it. And this is really where we talk about managing configuration items, or CIs. So the derived objects are the things that we build. They're essential configuration files. There are other runtime dependencies. All those things you have to consider when you build your production system. And it's important to create what's called a manifest, or bill of materials. That lists all the things that you're pushing to production. And we create cryptographic hashes. That's actually kind of a cool technique, and it's part of this whole verifiability technique. So Max SHA-1 or MD5, actually, I should say Max SHA-256 or MD5, are two of the commonly used cryptographic hashes. We calculate those hashes during the build time for each CI, which should not change, or what we call immutable. That means that I'm calculating a checksum when I build my code for each piece of the code. And when I push it out to production, I can recalculate those checksums and prove that the right code got to production. This technique is called baselining, and in industry standards, we also call it creating a physical configuration audit. And if you don't fully get the technique in the details, because I haven't shown you any code in this presentation, understand this. There are solid technical techniques that allow me to prove that the code that I built is precisely the code that is running in production. And then if it's tampered with, I can recalculate those checksums and identify the fact that something changed that shouldn't have changed. So cryptography is a key technique in being able to prove that the right code is running in production. Now, I once had a time in which I got called into a room and they told me that I had made a mistake that actually took down the whole New York Stock Exchange. Kind of an exciting moment in my life. I started wondering where I was going to be working next week. And fortunately, I had a set of scripts that calculated these checksums and verified that what I had deployed was actually in production. And that helped us identify the fact that somebody else had come along and innocently made some changes to the code. What I had deployed had been modified after I deployed it. So these techniques using cryptography, such as Max SHA or MD5, give you an approach that's fully automated that allows you to really be certain that your code that you deployed to production is there, it hasn't been tampered with, and to automatically identify if there is tampering, if the code has been changed. And then we're going to get into in a little bit how to self-heal your code. So if your code base is tampered with, how do you fix it? So continuous integration is another key capability. In continuous integration, many systems today are built by fairly large teams. It can be 10, 20, 30 folks working together. Uh, and you don't want to have people working in silos for too long because they're going to build, they'll build one piece of the system and it won't work successfully with other pieces of the system. So one of the best practices today is to continuously integrate our changes together and automate that whole build package and deployment of our code to create what I was describing before as verifiable baselines and deploy to test machines where we can run automated testing and verify those baselines on a continuous basis. So continuous integration is a set of practices that have become very, very popular and really help you improve the velocity of your development as well as the quality and integrity of your code. So continuous delivery, and we're going to talk about continuous deployment in a minute, but continuous delivery is delivering in small increments. It reduces risk. We typically may even deliver code that is kind of turned off, what we call toggled off or feature toggle. So we create less risk by delivering in tiny increments, and there's less disruptive behavior for the customer because the system's being updated in small pieces, but it doesn't really, we don't have to take the system down. We're not changing very much. It allows us to deliver in tiny increments, but actually to deliver more value, and it enables velocity. So continuous delivery is one of the techniques that's been very popular and very, very effective in the DevOps world. And it very much helps to improve both quality and reliability. Because if we deliver a system and we start doing some testing and verification, we realize there's a problem, we can quickly push out another fix and solve it in a solve the problem in a very, very short amount of time. Now, sometimes you have to be a little more disruptive. If there's a significant security risk or a critical fix, I can't be as gentle as I am with continuous delivery. And that's where continuous deployment means that I'm going to push out my changes, ready or not, here I come. So if we discover a library has a security vulnerability, even if that means I've got to take down the system for a few seconds and or I'm going to move something on your screen, ready or not, here I come. I've got to push this fix out right away. Now, this leads us to self-healing code. With self-healing code, I'm using those cryptographic hashes that I talked about before to verify and prove physically that the right code is in production. This is a similar technique if I've got hardware to make sure the hardware is working as expected and it hasn't been tampered with, right? Chips can be removed, hardware can be tampered with. So we verify that the system is working as it should be, and we can identify automatically if there's any unauthorized changes. We can respond to any changes to the baseline, and we can actually just slap on the correct version of the code if it is tampered with. So this enables us to create what is effectively self-healing code. So how else can we address issues? Bad things happen, right? Mistakes happen. It's not unusual for there to be some sort of an incident or a problem. So it's important to be able to respond to whatever sorts of issues come up. So there's a technique called incident management, in which we identify and we manage incidents. If something bad happens, if some problem occurs, how your users are really impacted depends upon how well you manage and deal with those incidents. So we communicate to all stakeholders, we organize the response, we focus on getting us back online fast, and we learn some lessons like what did we do wrong? Did we run out of disk space? Did we run out of memory? Did some folks miss some messages that were popping up? So we understand why incidents occur, and then we try to make sure they don't happen again. So this closely related to incident management is really trying to focus on improving our process. What went well? What could be improved? Creating a roadmap to get from where you are today to where you want to be. So when an incident occurs, you should be immediately thinking about, well, okay, this happened. What are the lessons learned? How can I make things better? And it's very much all about understanding the underlying events. So I might have been running out of disk space. I might have had a system that started going a little slow because I just don't have enough horsepower underneath the system. So understanding those events, some of them are going to be significant. They may very much predict an upcoming incident. So managing events happen. Managing events is very much part of uh, being able to respond to any kind of problems that occurred. But what do you do when you don't know what happened? So a lot of times you have to do a little bit of root cause analysis, and that's when we talk about problem management. Typically, we're getting some smart people in a room. We're trying to understand, well, why did we run out of disk space? Are we not cleaning up our logs? Did we suddenly get a whole lot of extra? Sometimes it's it's a matter of your system's been penetrated by a hacker who actually dumped extra payloads on the system to try to disrupt you. So that root cause analysis is very much important. And it might require that we change our procedures, including something called deprecation that most folks don't even think about. If I have code that is no longer being used, it might make sense for me to retire that code. And that's called deprecation. So one large financial services firm called Knight Capital learned that lesson the hard way. They had some old networking software that was no longer being used, but it was still running on the system. And it was part of the reason that they had a serious outage that caused them to buy $7 billion of stock they did not want, they could not hold on to. And they ended up actually going out of business because they took such a large loss. And it happened very, very quickly. And it was all because they didn't remove old, unused code. So deprecation, and in many organizations, you can't just delete stuff. You have to archive it for traceability, for forensics. So deprecation is this art form in which we remove code that is no longer needed. It's no longer running. We make sure it can't run. We can't make sure it can't create defects. So deprecation is often forgotten about, but it's a key aspect of being able to create secure and reliable systems, because that old code is probably vulnerable to attack, especially if it's still running. So how do we improve? Well, continuous process improvement is, well, continuous. You have to make sure that you consider all stakeholders, so be inclusive, be open about, what happened. One of the most important things that I focus on as a practitioner is making sure that everybody on my team is comfortable admitting that they made a mistake. Learning from our mistakes is very, very important. If folks are afraid to work in their environment, this is going to directly impact the quality of your system and your security. If folks are afraid to admit they made a mistake, then that's going to very much impact your system. So the people side of this, making sure that we learn from our mistakes, we create a culture where we share knowledge, we share information. We're not afraid to admit if we drop the ball, and everybody works together when something bad goes wrong. That's a key part of how we improve our process. One of the most important considerations is how we do what are called retrospectives. So after something goes wrong, sometimes folks call this a postmortem. In Agile, we have a kind of a healthier view. A postmortem is usually focused on, we had a system outage, uh, bad things happened. Even the word postmortem kind of gives you that sense. A retrospective, usually we start with what went well, what could be improved. It's a little more positive approach to things. Um, and it really facilitates that open and honest discussion. It's an opportunity to improve the process, drives the entire, not just the release process, the whole software delivery process. So retrospectives are a key part of this. And, DevOps is, just returning to that, it's this group of concepts. It's been around for a while. The use case is compelling. It's stimulating a discussion, and it's very much all about value. So I want to be able to deliver value to my customer fast. So velocity is really, really key here. But at the same time, think of a roller coaster. Lots of folks, love to go on roller coasters, right? My grandmother used to love them. Cars got to go really fast. Well, you want it to go fast, but you don't want it to fly off the tracks, right? So it's very much the kind of consideration. You want to go fast, but you don't want to have your system crash because you made a mistake. So DevOps is this approach, and it's a set of concepts. It's very much a culture shift. So lots of folks try to say it's only a culture shift. I think that's really being overly simplistic. There are some solid techniques like continuous integration, continuous delivery, continuous deployment, lots of other techniques as well. So it is a culture shift, a way that we look at how we're going to work together, as well as a set of techniques. And it's all about delivering value. So when I when I consider value delivery, I very much try to understand, what does a customer want. Remember, I talked to you about in the beginning, Duran and Deming, thinking, what is a customer value? What do they need? We want to improve quality and security. We also want to deliver a lot of features fast. People are always asking for new features in a system. And systems that impact people's lives are rightly often governed by federal laws, regardless of what country you're in, whether you're in the United States or in Europe or in many other countries as well. There are laws that create what are called regulatory requirements. So if you're in the banking system, it's not acceptable that you go Saturday night and you want to go out with your friends and your credit card doesn't work because the bank blew a release and their ATMs are down throughout the whole city. That's can be an issue. And the banks have to explain why they have had outages, particularly if they didn't follow accepted practices. And that's a lot of what we're talking about today and a lot of what industry standards are focused on. So regulatory requirements ensure that missile systems are developed in a responsible way, that life support systems used in hospitals to help keep your loved one, if your loved one is using a respirator, you want the firmware that was used on that medical device to be developed and tested properly, to be high quality. So regulatory requirements start to get to what is corporate responsibility for delivering reliable, secure, and defect-free systems. And the truth is, we know how to do this. We can deliver 100% defect-free systems. We can deliver systems that are reliable and secure, that can self-detect if they're tampered with. We discussed that. That can actually self-heal. So regulatory requirements are going to start to get into, how do we actually enforce this? So one of the most common is Section 404 of the Sarbanes-Oxley Act, what's called SOX. The old SAS 70, the Office of the Currency, the FDIC, FINRA, all of these industry regulatory bodies have got rules that organizations have to follow. In the medical field, it's HIPAA and CFR 21. So there's many different types of regulatory requirements that set the law, but then, well, how do I do it? So I've alluded to a lot of the ways in which you do it, but in our world, we have to use what are called industry standards and frameworks, which give you the guidelines to understand in more detail what you have to do. Now, most industry standards and frameworks operate at a level where they explain what to do. Let me give you some examples of how. I'm always a guy that's trying to push to get to the how and make this a lot more clear for people. But typically they explain what you have to do and they allow you to, a little freedom in terms of how you're going to do it. But these are some of the common standards. I'm going to go into a little more detail about it. But I also want to mention that there are frameworks. So for example, COBIT or IDLE, even the old CMMI, less commonly used today. So there's a difference between the way frameworks are developed and standards are developed. Standards are typically voted on, and there's a whole validation process. I've been leading an effort to create an industry standard for DevOps. That's P2675, and we're going to talk about that in a little more detail in a minute. But then you're also going to see that I've been talking about it throughout the whole presentation. And we're starting to impact other industry standards on an international basis to help the testing standards, the risk standards, all of these different approaches to get better at developing reliable and secure systems, because you have every right to expect that banking system to be 100% reliable. You have every right to expect that a life support system is 100% reliable. I've taught these techniques to nuclear power plant engineers. Their whole culture is focused on 100% reliability, because if they make a mistake, it's a nuclear meltdown. There's no room for error in many industries. And the truth is, we can do this. We can create systems that are 100% reliable, secure, and defect-free. We just have to take the right approach and put in the right effort. So 828 is the configuration management standard. I co-authored that one. Its competitor is EIA 649B. ISO has many standards, including my oldie but goodie 9003, which supports the quality management system. There are full lifecycle standards that take you through requirements and testing and design and development, and they're very comprehensive full lifecycle systems. They're so much fun. There's lots and lots of guidance to take you through the whole lifecycle. What I usually do is grab a beer and spend a Saturday night reading them. So just kidding. And 2675 is an emerging standard that is just been voted on. We're responding to a few comments. It's really it's available in draft form right now from the IEEE. And that is, we expect to have quite an impact. So 2675 is a DevOps standard for building reliable and secure systems, including application build, package, and deployment. And I quickly took you through what build, package, and deployment means, right? You take your source code, you create runnable objects, you package it, you use cryptography so you can prove the code really got there. Its purpose is to specify required practices for ops, dev, and other key stakeholders. So DevOps is not just about dev and ops, right? Don't forget information security. Don't forget your end users. It helps them collaborate and communicate to deploy systems and apps in a secure and reliable way. Now, a lot of what I focused on as I was explaining this is that different people have different perspectives, right? So development wants to go fast. Operations wants you to be reliable and secure. How do you balance those different perspectives? Well, information security has a perspective. Sometimes those guys come in and the information security team's been kept in the dark the whole time the system's been developed, and they come in with requirements for security that are just seem completely out of place. They haven't been included from the beginning of the process. So one of the things I said is you really have to do this from the beginning of the process. You can't tack on security at the end. If you include your security team only at the end of the process, it's not going to work. You won't have a secure system. So key aspect of this is to left shift, start doing the right thing earlier in the process, include all the right stakeholders, collaborate and communicate and understand we all have different perspectives. And it's not just about the applications that we write, that we build. It's about products that we purchase off the shelf. It's about the underlying operating system that we're going to run. And if we take this full life cycle approach and include the right stakeholders, the truth is we do know how to build very reliable systems that have great features and are quite secure. So the scope of the standard is to specify practices for all the different groups, DevOps and other key stakeholders, collaborate and communicate effectively to build, package, and deploy systems and software in a reliable and secure way. All of these activities and functions are integrated within the complete life cycle. So this emerging standard for DevOps really takes this full life cycle approach, and in particular focuses a lot on how to do left shift in a very practical and reasonable way. So you should take this information, create your own plan for improvement. Consider what kind of training you need. What's the, how are you going to use source code management? How are you going to use build automation? Understanding how to use continuous integration or a CI server such as Jenkins or many of the other ones that are out there. Automate your whole build, package, and deployment, and create procedures so that you can do that physical configuration audit I was talking about, where you verifiably prove that the right code is in production using cryptography, such as MAC-SHA-256 or MD5, and identify if the code is tampered with, and then be able to effectively self-heal your code if you need to. So you have to kind of create your own plan of improvement. What I usually do is ask what's going well, what could be improved, and I help the team understand that delta, how to get from where we are today to where we want to be. But the fact is we can create reliable, secure systems that are 100% defect-free if we left shift our entire process, where we're considering quality from the beginning, We're considering security from the beginning. We're getting information security involved from the very beginning of the process. And we're really considering this as a full life cycle. So now please feel free to link with me on LinkedIn. My LinkedIn is, on the screen, LinkedIn/in/Bob Aiello, BOBAIELLO. Make sure you indicate in your invite that you attended my class. Come down to my website, Agile ALM DevOps, and I hope to be in touch with each one of you. Thank you.